So welcome back to this session on a new topic, which now is going to deal with recurrent neural networks. So last week we went through CNNs and how to write our own codes, and also how to write our own codes using PyTorch and TensorFlow, which are standard libraries, and many of you will most likely use one of these two libraries. Now, what we're going to do today first is to give you a kind of bird's view on what is going on with the RNNs, or recurrent neural networks, why they are interesting, and we are going to lay the kind of foundation for the mathematics of recurrent neural networks, which we will discuss in more detail towards the end of this lecture and also next week. And next week, we will also discuss how we actually write our own code on RNN. So not only using PyTorch or TensorFlow, but in the beginning now, I will give you an example using either TensorFlow or PyTorch so that you can see the basic setup and how you can actually use these popular libraries in writing your own code for a recurrent neural network. Now, the lecture notes, which we normally recommend, is to take a look at the Goodfellow's text. And chapter 10 here contains a lot of the discussions and the basic architecture of an RNN. Rashka's textbook has a very nice chapter 14 here. No, it's actually chapter 15 with a GitHub address as well. So you can download the code examples which are discussed in chapter 15. And then there are also some TensorFlow examples if you're interested in that, in the textbook by David Foster. Now, the one by Babcock and Bali has a stronger focus on generative methods, which means that the way they treat recurrent neural networks and convolution neural networks is often done in a very brief way. And essentially, you will find that type of information in the first 2 to 3 chapters. But their main focus, as the text says, it says generative methods, whereas the Foster's text spends quite some time on the discussions of recurrent neural networks. And there are many nice examples which you can look up there. Now, if we, just to give you a kind of overarching motivation for why these are interesting things, if you think of a standard neural network, the way we have been discussing them, and the way you have studied them in different courses, one of the limitations is that they're not designed to handle sequential data. So sequential data means that you could have a time series, just to give an example. Now, in the examples which I will discuss here, most of the examples will actually deal with solutions of natural science problems, which are typically of the type you solving a differential equation, or you having some time series as data. However, you should keep in mind that CNNs, now RNNs, they form the basis for many of these large language models. And they've actually been used widely in sequencing strings of text so that you can actually use them to make a translation to another language. So they're widely popular for these kind of applications as well. And you will thus find recurrent neural networks as being used as a kind of input to studies of large language models as well. And if you go into the textbook by David Foster, you will find examples of that. And the same in Rashka's textbook. Actually, in Rashka's textbook, you will find more applications dedicated to topics outside the natural sciences. So the kind of limitations with a standard feed-forward neural network is actually it doesn't have this kind of capability of storing information about previous inputs. And that's typically what you would have for time series. If you measure, let's say, the heartbeat of a patient, you can look at how that develops over time. If there are any arrhythmias and so on, these are typical examples of an experiment which you can run. So a typical recurrent neural network, as opposed to a fully regular connected neural network, which we often write just as FCN or just NN, that has layers that are connected to themselves. So that's a big difference. Now, if you go back into the content of this week, you will find the slides here, but you will also find the slides about the mathematics of recurrent neural network. So that's another Jupyter notebook, which we will also partly discuss next week. But if you think of a drawing of a neural network, what you would have if you think of a neural network, the standard way you've been studying them, is that you have basically no connection between the nodes in a given layer. That's a standard feed-forward neural network. On the contrary, if you look at a recurrent neural network, and we are coming back to that setup, you can have connections between layers at a given, what we will later call loosely, for a time step. It doesn't need to be a time step. It could be an observation you make at a specific point, one, a new observation at a point two, etc., etc. But now you can have connections between the nodes in a given layer. And that is different from what you have in a standard feed-forward neural network. So these recurrent neural networks, they're actually tailored to deal with sequential data. And in a certain sense, that is data that is ordered, data where the order matters. And in a regular fully connected network, the order of input doesn't really matter. Another property is that they can handle variable input and output. And this is something which is normally different from a standard feed-forward neural network. So if you think again of a breast cancer data set, which is many of you have encountered, this Wisconsin breast cancer data set, which has something like 30 features. So if you have trained a regular feed-forward neural network with 2 of the features, it makes no sense to suddenly add a 3rd feature, and the network will not know what to do with it and will just reject such inputs with 3 features or any other number of features that isn't 2 for that matter. Now, one of the problems you face with recurrent neural network in the training, and this is something which we will see pretty soon, is the problem of vanishing or exploding gradients. And this is a delicate issue which one needs to tackle, and we are going to discuss different recipes for dealing with that. But first, I wanted to have you with me in understanding why the gradients can actually explode. So till now, till last week actually, our focus has been on a convolutional neural network for imaging in particular, or a feed-forward neural network. And the output or the activations flow only in one direction. A recurrent neural network, it looks very much like a feed-forward neural network, except that it also has connections pointing backwards. That means that you can store information about previous times. And that becomes very important for many, many applications in science. So it's not only something you can use on sequential data, but they also have been used besides sequences with strong interdependencies. It has in particular been used successfully to study language models. Okay, so the thing I wanted to do is to start with a simple case, which is the solution of a differential equation. And I'm going to use that to illustrate the basics of a recurrent neural network. So, and then from the simple differential equation, we are going to make our abstractions. But I hope that example with the solution of a simple differential equations helps you in gaining a kind of conceptual understanding of what a recurrent neural network is doing for us. Now, what I've also plugged in the beginning here now is to give you a simple example using either TensorFlow or PyTorch. This is just to get us started so that you see the basic ingredients you would have to add. And then we're going to demystify it and set up all the mathematics which is needed. And next week, we will discuss our own codes for making a recurrent neural network. A recurrent neural network can also be used as an ingredient in more advanced methods, like generative methods. So when we come to Boltzmann machines, you could actually have a convolutional neural network as an ingredient in a Boltzmann machine, or you can have a recurrent neural network as an ingredient. So many of these things which we have gone through, like a neural network, a convolutional neural network, a recurrent one, etc., they can be seen as basic building blocks for further models, which we're going to discuss. So after we've done with recurrent neural networks, we will discuss autoencoders. And in autoencoders, we can have a standard feed-forward neural network, or we can have a recurrent neural network if we want to. So everything we do here can be actually thought as building blocks for, let's say, generative methods or other deep learning methods. So if we now look at the example here, besides this imports, etc., this is a simple case where I'm now taking a function, a sine function, which you can see here, and I add some random noise to it, which is pretty strong. And as you can see, I run it for 1,000 points, and I have a step size of 4 between each 1,000 points. So when I'm plotting, visualizing things here, this is my step size for the visualization. And the training points are the first 800. So think of you training a network on 800 points, and then you use the remaining 200 to make a prediction. Now, if I now want to set up, so you can see here my, this is just me setting up the data. So I'm using Pandas. As you probably know, I mean, Pandas is extremely popular software. Then I set up my train and test sets. And the test set or the training set goes from 0 to 800, and the test set goes from 801 to 1,000. And then I'm just setting up the train and test. As you can see here, I reshape my data set, and then I make a model. So this is my recurrent neural network. And the simplest one, which uses an algorithm we will discuss in greater detail next week, which is called backpropagation in time. So the backpropagation algorithm pops up again in training the weights and the biases, except that now we are actually we have to do this at every time step. So time here can be seen as a given variable, which could represent time. So when I say time, this could be data which represents measurements at given time intervals, or it could represent you measuring the position of an object in one place, then in the next place, etc., etc. So in this case, I'm setting up a simple recurrent neural network where I have an activation function like a ReLU, and it has 32 units, one hidden layer only, with 32 units. This is what I define here. Then I have a dense layer, and then I have a new dense layer where I output the results. So my mean squared error is the output, and I use an optimizer, the root mean square propagation. And you can see now the summary of the model. This tells me now how many parameters I have to train. And this is the total number of parameters which are trained in this pretty simple network. Now, we are going to discuss in more detail how we write our own code in order to demystify what many of these entries mean. But when we now discuss the basic setup, we are coming back to what these parameters actually mean. Now, if I now run the calculations here, you will obviously see that since I used a function with a lot of noise, so the blue line is actually my data set with a sine function, and the orange one is my prediction. Now I have a lot of noise here. If I now, on the other hand, go back again and train it with no noise, hopefully then my prediction should look much better. So I have a lot of noise here, as you can see. It's 2 times a random number, which is distributed according to the normal distribution. So if I just rerun this simple example here, the number of parameters are obviously the same. So I'm running through the different epochs and calculating the loss function at the different steps. So every step now can be thought of you making a measurement. So let's just go through here. Take some time. It's not. So let's just let it run through. And you can see that the loss function is roughly 10 to the minus 5. So this is a pretty good prediction which we're making between a sine function and what a recurrent neural network has been trained to reproduce. So let's see if it's done. And now you see that my blue one is actually my originally sine function, and the orange one is actually my prediction. And that means that I train up to 800. So you can think of every time step here, every step here as a time you make the measurement. It doesn't need to be time, but I'm just using time loosely here as a variable, okay? And now I train it up to 800, and what I have between 800 and thousands is my prediction. So when you have a well-behaved sequences like this, you will often see that recurrent neural networks do a pretty good job. Now, an alternative here to a sine function could be you solving a differential equation. And then you use, let's say, the first 100 solutions as a function of time as input to the training of a recurrent neural network. And then you use the recurrent neural network to make a prediction beyond what you trained it for. You see the picture? So that means that suppose now you have a differential equation solver, which is a fantastic one, which does a pretty good job in solving a set of equations. However, this differential equation solver is very expensive. It requires a lot of CPU cycles to run, but it gives you a good result. So then you could say that you run this differential equation solver for, suppose, 100 times. This is the data you could train a recurrent neural network on. And then you would use the network to make a prediction for times which you have not found a solution from with your differential equation solver. That's one possible application. So what you're doing then is actually to use a recurrent neural network as an extrapolator. You use it as we did here. So you could say now that I could train my network only to 800 and then look at the rest as an extrapolation. But in this case, since I have the sine function, I'm just making a comparison with the sine function. And you see that my extrapolation is pretty good. You can, and this was a very simple model, a very shallow network. So you can make it more expensive by adding more parameters. But in general, you see now that when you have something which behaves nicely, it's very easy to use a recurrent neural network as an extrapolator. If you're doing weather forecasting, then temperatures can oscillate much more. And then it can be difficult to extrapolate. And some of you are actually looking at weather data, and you've seen that you can do a pretty good fit to the data you trained it against. But then when you extrapolate, you may not be able to catch all the fluctuations which are in the real data, as you saw with the random noise which I added here. So there is a similar example with the PyTorch, and I'm not going to go much into detail to that one, but that also generates a sine function and splits into training and, in this case, a validation set. So it's pretty close to what we had before. You create a custom data set for sequence generation. You define a recurrent neural network with one recurrent neural network layer and a final plain linear layer, like the one we have here. So you're just outputting a function value. That's your final output. And you train the model using the mean squared, which was the same I used here. So the loss which you see here is just the mean squared error. And then I use this to make a prediction. And in this particular case, the function is actually not that different. So I have an RNN model. The names are almost the same. So this is my NN RNN here. And I'm using a linear layer at the end. So it just outputs the results like you would do with a neural network when you are fitting a function. And it has the feed forward part. I'm setting up the model I am setting up the loss function, which is now the mean square error, and my optimizer is the Adam optimizer. So these are just examples which I took from the text of Rashka and just adapted it to this specific case. And here we are running things with just one learning rate. So the learning rate is obviously also a parameter which you need to set. And then it runs through a set of epochs. It does a validation, it calculates the loss here, and at the end, it makes a plot. So you can see the training here, the loss is pretty small. And at the end, this is just the distinction between the training loss and the validation loss. And you can see now that for the different epochs here, when I reach something from 20 epochs and up to 100, I basically get results which are pretty close to each other between the training and the validation data. So when you're fitting something as simple as a sign, a recurrent neural network does actually an excellent job. So they're very powerful in general because they combine two properties. You have hidden states, which allow them to store information. So you can actually store information about the time evolution, and especially about the past in a very efficient way. And you have linear dynamics that allows them to update the hidden state in a complicated ways. So this is one of the claims. So what you see here is a typical claim you will find in the literature with enough neurons and time, which they had. You can train almost everything. However, they are problematic, and one of the problems is actually the one with exploding gradients. They can oscillate a lot. They can behave even chaotically. But it could also potentially learn to implement lots of small programs that each capture a nugget of knowledge and run in parallel. The extensive computational needs make them often hard to train. And that's one of the drawbacks of a recurrent neural network. So what I wanted to do is just to break down the pace a little bit and take a look at some basic and simple equations and illustrate the way we are going to set up a recurrent neural network. So this lecture, I want to keep it at this kind of a top-down view of it. And then when we get towards the end of the lecture, we are going to dive into the more mathematical details of how you can write your own code for a recurrent neural network. There are some of you who actually are doing that, who have a project where you write your own RNN. But in general, most of you will actually use either TensorFlow or PyTorch. So if you don't have the time or are not interested in writing your own RNN, just use the functionalities of these libraries. So let's switch pace a little bit and switch over to the whiteboard. And let's try to make an illustration, which hopefully many of you have seen. And we're going to start with a famous differential equation. So building our understanding of an RNN, our view of a recurrent neural network. So we're going to start with a famous differential equation. An ordinary differential equation is actually a second order. So ODE stands for ordinary differential equations. And this is an equation which many of you have seen. It's a one-dimensional equation. So this is the acceleration in Newton's law. We have a velocity-dependent term, which you can think of as a drag term or resistance or friction term or whatever. And then we have some kind of oscillatory motion. So this X is time dependent. So if you look at the harmonic oscillations, what you would have then would be an equation of this type. And this depends on time. This is an applied force. So normally, when you look at Newton's law, you would not have this term. This is a friction term, a damping term, as we call it. And you would normally not have this one, which can be thought of as an applied external force. So if you think of the pendulum which you meet when you enter the building here, then that pendulum, the differential equation for that, will have, instead of an x here, it will have an angle, theta, with respect to a given axis. And you will have a sine theta as a function of time. There is obviously a damping term due to the air resistance. And then there is an external force which makes this pendulum swing back and forth. And you know that if you apply or solve this equation, what you would typically find then, if you look at the first term here, this is a damping term or friction. This term which you have here is just an applied force, applied external force. And this is just the acceleration in Newton's law. The damping is normally proportional with the velocity, with v, which is dx dt. And the x term is what comes from harmonic oscillations. And this is something which you probably are very familiar with. Now, the common strategy when you solve this equation, which is a second order equation, is to rewrite it as two coupled first order equations. That's the common solution strategy. And we are just going to look at one of them. So let's look at the velocity. So the strategy when you have a second order differential equation is to rewrite that as two coupled first order ones. So you would have now a differential equation for the velocity, which we know is just the change in position. And then we have an equation for the velocity, the first derivative. So this is the acceleration term, plus this constant, v eta, which can be a material-dependent constant or air-related constant, plus x. And now I'm skipping the t dependence here. So these are two coupled differential equations. And then we would also have some initial conditions, some x of t0, which we often would call x0. These are the initial conditions. And then we have some v of t, and this is something which we call v0. So when you look at these two equations, it's pretty common then. So if we now do a small rewrite, we divide by the mass of the particle, and then we get this as an equation which we call minus eta divided by the mass. We have the velocity term, minus x divided by m, and then we have plus this force term divided by m. And now we can scale away these parameters like the mass. So just for simplicity now, we could just put mass equal to 1. So this is something you would typically just scale it away by some rescaling of the parameters. But we could now just define a new parameter, say that mass is equal to 1. And then we have a simpler equation. Now, the way we solve this is that we discretize the velocity and the position and time. So we'll discretize. So that means that velocity goes over to some v of I, which is the same as v at the time t of I. And the position goes over to x of I, which is again the same as t of I. And time has been discretized. So you would typically have a time t of I, which is given by some time, initial time t0, plus some step size in time, multiplied with this constant I, where I goes from 0, 1, up to the final time, which is n. And this delta t is then simply given by t of n, the final time, t0, divided by the number of points you have used in the discretization. So this is a common recipe, which you probably have seen many, many times. And I hope you don't get offended if I repeat some of the basic things here. Then when you've discretized the equations, you can use a famous method, which everybody probably has met. And that's Euler's method, which is the simplest possible one, but that's going to serve for us as a way to introduce the basics of a recurrent neural network and the way we think of a recurrent neural network. So if you do that, we have an x of I plus 1. So the next time step of x of I plus some delta t times v of I. And we have the same for the velocity, which is given by v of I plus 1, which is given by the previous velocity. Sorry, I have a little bit delta t. And this is multiplied with the derivative, which is now f of I minus this parameter eta times v of I minus this parameter x, this position x of I. This is Euler's method. So I put an equality sign, but it's actually an approximation because we have made a truncation in delta t where we leave out all the terms which go like delta t squared and higher. So that means that in principle, I should just put an approximation sign here, but I'm just going to leave that out. And now I just drop position and I just look at velocity. So look at velocity now. Look at v only. What I can do now, I can rewrite this equation. If you now take this second term, which we have here, I can think of this as a specific function. So I can rewrite my v of I plus 1 here as a v of I plus some function f, which depends on v of I. It depends on x of I. It depends on delta t, and it depends on f of I. So f is now just some function, which in our case is actually what we have here. But just think of this as a function. Now the way we can do the visualize this is in a graphical way. So if we now look at this equation, now we're actually going to make the first step towards us rigging up the basics of a recurrent neural network. So let's do that. So what we have is a dynamical system which is driven by some external signal. And we can always plot it graphically, what we are doing now. So you could think of the following graphical representation. So let's do that. So that means that we can now think of a box here, which we just call for F0. And that receives as an input some uppercase F0, this is the external force, some position x0. And then we are feeding into it some V0. So that is fed into it. Now, this produces a new result, which is our updated velocity, V1, which we then in turn feed into a new function, F1, which then gets an input F1 and X1. So these are then quantities which we can think of as external inputs to the process of measuring the velocity. And you see that this can just be continued. So we get a V2, and it goes all the way down to a final time, which we just call f of n. So this is our final time of fn of xn, and that produces the final velocity v of n. So this is just a very simple graphical way of illustrating these equations. But now we can just make this a little bit more fancy. So the way we could think of this now is that somebody gives you a fancy differential equation solver. But at every time step, you are measuring the velocity of this object. So you give the system an initial velocity, an initial position, and then the system evolves over time. But then at each time step, you actually measure the difference between your lovely model and an observation which you make. So let's write that in a graphical way. So think of this now as a specific observation, and we are starting with V0. This is our initial velocity, and that is also our initial observation. So this takes place at t0. Now, we are having, so let me just place this in the middle here, so I get some more place. So I have my initial velocity, v0. This feeds into this function f0. Now, it gets an input of f0, x0, and then it produces an output at this time step, which is the velocity. And so we're going to write it like this, and this is going to be my v1. This is what it produces. Now, this is then fed into a cost function or loss function, which I'm going to call L0. And that could be the mean squared error. But then what I feed in here is something which I'm going to call V1 observation. So that's my experiment. So I observe the velocity of the object, and then I'm asking myself, is this going to be a good model or not? Now, this output here, V1, then goes into the next step, which is my F1, which then also receives an input F1. It receives an X1. It produces a V2. So I actually have, this should be 1 here, L1. And then this V2 here, this is inputted to L2, where we then make a comparison with the V2 observed. And this is something which then would continue all the way to the final time, the F of n, and then we have an Fn and an Xn here. And this produces an output, which is my V of n. It then produces my Ln here. And then I have my final observation like this. So suppose these are real experimental measurements. So what you could do then is to define a total loss function, which is now the function of some parameters. So you could think of this L of I, where I goes from 0 up to, or I equal 1 up to n. And this depends on some parameters theta. Because now I could think of optimizing this function so that I can feed back to my model and find a better fit next time I do the calculation. So you could think of now of you wanting to optimize the model I have given you. Suppose that model has some parameters. And you think that your model is a very good one in reproducing the velocities, but there are some parameters which can be tuned. So what you could do then, for every such step here, is that you now calculate the difference between your observed values and the calculated one. And then you accumulate all these values. So this will be your feed-forward stage. Now you can do, since you're familiar with backpropagation, you can do a backpropagation in time and calculate the gradients of these functions with respect to the parameters theta. So this is something which you could actually call a digital twin. Actually, this is much of the recipes which is used for a digital twin. So think of a windmill park. A windmill park has often been tuned finely to the outer pressure, to the wind direction, the wind speed, temperature, etc. So there is a theoretical model which says that the windmills should be aligned in a specific way because now the wind is coming from the southeast in order to maximize the production. So what you do then is, for instance, that you have some observations. So this windmill park has tons of sensors. Actually, without sensors, machine learning would not be where it is now. So the sensor industry is essential because the sensors then tell you that maybe if you tilt a little bit the angles here, you can optimize the output from the windmill park. So that means that there can be some feedback where you correct your output from the model and look at the observations. So in that case, V here could be the power which is being outputted by the model and compared with the real power which the windmill park is producing. Because this is one of the parameters which would feed back to your digital twin. So that means that you could now try to optimize these parameters in your theoretical model so that you actually get the best possible power output of the wind park given these meteorological conditions. So you see the philosophy here? So the backpropagation in time is you actually having observations at given time steps, and then you want to propagate back and try to update your model so that you get a better reproduction of the data. So what you have here, even if we started with a differential equation, is a kind of basic model for a recurrent neural network. Any questions so far? Does it sound okay? So let's look at the way by which you can simplify this further, because now I'm going to change notation a little bit, and we are going to replace this function f, which may be a known function, with the hidden layers of a neural network. So I'm just going to change the names of variables, because if you now look at what we have here is, by the way, this image which you see here, this picture here, is something which normally can be shortened to something like this. So you have a function f, you have some input v0, you have some output at the end, v of n, and in between something happens. So these are different types of operations on the system. So this is a typical way by which you would write this network in a more compact way. So let us now, with this kind of preliminary models or views on it, we can now set up a simple RNN. And what we are going to do now is to make a change of variables. So if you now look at this v of I, which we had, v of I, which was equal to v of I plus 1, which was equal to the previous value, plus this function, which now depended on f of I. It had a dependence on the previous value, v of I minus 1. It depended on x of I, and it can depend on further variables. What we can do now is simply to say that the whole thing here is a function of h, which we call h, and this function depends then on x of I. And what I'm going to do now, I'm going to skip this f of I for simplicity. So x of I is just some input. In our differential equation, it is the position. But now let's just call it x as an input to the network at a given step. So it will depend on that. It will depend on the new value, the value v of I, but it will also depend on the previous values here. It will depend on v of I minus 1. And what we could do then is simply to replace that one with some function h of I minus 1, and then there can be some further dependencies. So what we are going to say now is that this v of I plus 1, and we are going to call this function here for some h of I. So we would have a v of I, which is then e plus 1, which is then given by this function h of I. And then we have our v of I, which is then given by a function h of I minus 1. So this function here is going to replace that value. So I should put an equality sign here. And then there can be more variables if we want to. So what that means if we now make a small change of variables, I'm going to change things a little bit. So I'm going to let this v of I, I'm going to let that one be replaced by an y of I. And this is what you typically will encounter in different textbooks. I will keep the x dependence. And this is the output. And then these functions h, which I have, I'm just going to keep them because they are going to represent the layers of a neural network, or just the layers of this recurrent neural network. So what I'm going to have now is some input variable, which I'm going to call y0. This feeds into this h0. So this is what my network is output having as a complex function. And it produces an h1, a y1. This feeds into an h1, which then gives an x, has an x1. It produces a y2 here. And this continues all the way to the final point, where I have an x of n, and this produces a y of n here. So this is my output of the network. Now, after the break, we are going to make this a little bit more complicated. And we are going to add a cost function, and we are going to add parameters we want to compare it with. So what you could think of now, if you go back to that simple sine example, is that this could be the network which has been trained to reproduce a sine function. And in every step here, we compare this output to the sine value. So in here, this variable here is going to be input into a loss function. And that loss function is going to have some y observed here, which is going to be compared with. So after the break, we're going to set up the final model with the parameters which we need to train. But the whole philosophy which you see in this example here is the kind of basic philosophy which is used in a recurrent neural network. However, every thing which we do here, this h0 connected with h1, is going to have parameters which we need to optimize. And these are going to be the weights and the biases. Furthermore, these x's, which you can think of as an external input, is also going to have some biases and weights which are trained and connect x0 with h0. And then similarly, h0 here produces an output through an activation function, which also has some weights and biases which connect the output from the network here. So this here doesn't need to be just one node. It could be many nodes. And it could also contain many hidden layers in the training. So we're going to see that more pictorially after the break. But after the break, we are going to introduce weights which connect all these different points. And that's the way we keep information about the history of the system. And you see immediately that this is going to become expensive from a training point of view, because if we have 1,000 time steps, for instance, that means that you would store, if you don't share the parameters, which is a common approximation, you would then have to store huge amounts of matrices as you keep training the network. So a recurrent neural network in its simplest form, in this connected way, is an expensive object to train. And that's why there are many, many tricks or ways to reduce the amount of training, like what is called weight sharing. So that means that you only train the weights on some specific time steps, and then you use the trained weights for the rest of the calculations. We take a small break. About 15 minutes, is that fine? Yeah, let's do that, right? And please feel free to ask questions if you have. So welcome back again. The thing we are going to do now is simply to set up this drawing, which you see here, in a more detailed way. and to set it up the way it's going to look like when we have a basic recurrent neural network. So let's just extend this model to an RNN. So this is normally called a simple RNN. And a simple RNN is normally trained by what's called the back propagation in time. So when I'm saying time, you don't need to think of this as time. It could just be a sequence of observations where the sequence is not determined by time, but by another variable. So I'm very much focused on natural science applications, but keep in mind also that this is a huge field in language recognition and natural language processing. And the examples you find in Rashka's text are examples applied to language processing. Okay, so let's now make it closer to the way we are going to train the network. So instead of having a Y0 as input, I'm now going to have an H0. So that's my initial value for, let's say, the weights and the biases which need to be trained. Now, this H0 feeds in to something which I'm going to call an H1. Then I'm going to have some input X1 here, which feeds in here. So this could be you measuring the blood pressure of a patient. So X could now be that specific act of measuring the blood pressure of a patient. So you have some external probe, which then acts on a patient. Then what we will have next is that we are going to produce an output, which I'm going to write as a Y, like this. And then in here, we feed this into a box where I have my loss function, which I call for L1. And the value which comes in here is my target value. So I'm going to call the value I'm going to target with just a T. Then we are going to have parameters which link the different inputs and outputs of the network. So you can now think of the H's as some kind of hidden layer where these are connected. So we have a connection here where I'm just going to call W, H, H. These are weights which need to be trained. So they become the parameters of the theory here. And you could think of this H as just one hidden node or one hidden layer in a neural network with parameters. And then it connects to the next hidden layer. And we have a connection between X and H, and the weights and then later biases as well are going to be labeled with an H times X. And then here, this one is now going to be an H going to Y. So these are going to become parameters which we need to train. So the terms which you have here, let's just circle them in here. These are parameters. So this one, these are our parameters to be trained. We can obviously change these parameters from layer to layer, but now we're just going to keep them by the label W with a subscript HH, HX, or HY. Now, this feeds in, so there's a connection between the previous layer. So we're actually storing information about what happened in one. It could be time one. So that information is now trained into these parameters which you have here. Then this feeds into H2, which can have an external probe, which acts on the system, which sends in some input X2. Then it produces an output Y2 here. And this one feeds in to the loss or cost function, which I'm going to call L2 here. And now I have space here for a T2, like that. And It shouldn't come as a surprise that this just continues. And we will have the weights again here, WHH, there will be a WHY, a WHX. This feeds into an H3, and this goes all the way down to an H of N here. And we have an input of XN, an input, an X3 here. And then we produce, just let's wrap up the figure. Of N. And this is going to be my L3. It takes an input, T3. It produces an output here, Y of N. And we have an L of N. And then we have a final target value, T of N. So the quantities which we have ringed in, these different W's, these are the parameters which we need to train. So we have a WHH, and this just continues. So these are the parameters to be trained. In the optimization. So a standard recurrent neural network has then obviously an initialization of all the parameters, and then there is a feed-forward pass. And the quantity which we are going to evaluate is obviously the total L theta, where theta are now the parameters which I'm going to list. And this is going to be the sum of all these L's from I equal 1 up to N of this L of I, which then will depend on the parameters theta, but it will also depend on the target values and the output of the network Y. That could, for instance, be the mean squared error, like the training we did with the sine function. Okay? So let's now look at the parameters and how we would set them up. Yeah. Yeah. So if you now look at these weights, yeah, it is. It is like a normal neural network, except that now, if you think of a neural network, then the nodes in one given layer, you can actually make connections. This one, H1 here, can have different layers, but you can also have connections between the nodes in the layer. So that's going to make a difference. And in addition, so it looks very much like a neural network. If you think of a neural network now, where you have all the different layers along the vertical line here, right? But the difference is that a neural network doesn't take an additional input. So the input is just given in the first input layer. But now you have some time-dependent perturbation of the system. And that's the difference between a standard neural network and not. And this perturbation here, or this input value, means that you can actually store information about previous times and how they influence the next time. And if these variables here are different from step to step, they will be able to encode complicated information about, let's say, the time evolution of the system, which a neural network normally never captures. So this is really tailored to sequential type of information. I'm coming back to that. So, hey, say it again. Yeah. Yeah. So if you look at this variable x1, this is linked with h1 through these weights. So since this changes, that means that if you think of this as a time sequence, then clearly every time step we have here will give you different weights and biases when you train the network. So in that sense, this external probe, which you are acting on the system with is something which then will contain an information about what happened at that specific time. And that's the way you would encode the information about, let's say, time in the training of the weights and the biases. So let me just write down the equations, and then we are going to look at further examples, and hopefully then it will be easier to visualize what is going on here. So if you now think of this hi, a given one, so a given h of I, that will be given by, this is an output for the hidden layer, which has some activation function, sigma. And you saw in the examples which we put up in the previous lecture, this could be the ReLO function, it could be the ELO or any of the famous activation functions. And this has some input, which we can call C of I. Now this C of I is now given by a weight matrix of Hx, which then links this X of I. So X can be a vector, and W can be a matrix, plus the weight, which we call HH, multiplied with the input from the previous layer, plus some bias. So this B is what we normally call the bias variable, in case these parameters W by accident happen to be 0. So that would be the way we define the input to the activation function. Then the next variable which we need is obviously a Y, an output, which is Y of I, which now has some sigma, and let's call this sigma of Y, with an input R of I, where this R of I is now given by this W, HY, multiplied with the output from the network, plus a new bias C of I. So this is a new bias. So it means that the parameters which we are going to have for one step, and this would change from step to step. We are going to have these parameters of WH of X, and then we have a vector B and a vector C. Now, there are many strategies, because you see quickly that if these matrices contain many different nodes which are linked together, that means that these matrices can quickly become very large. So the dimensionality of the problem explodes. So there are several strategies to actually reduce the dimensionalities which you see here. And one of the strategies, which is pretty common, is to use what is called weight sharing. Alternatively, you can truncate the number of steps where the different weights are trained. So you could, suppose you have 100 time steps, you could now train the weights and the biases for only the 10 first. And then you use the same weights and biases, assuming that the system doesn't change, then you can use the same weights and biases for the remaining 90 points. So another strategy is actually to truncate. So truncation of number of steps where different weights and biases are trained, where different weights and obviously biases as well are trained. Now, the way the training is done is as follows. It's done in a sequential way, in a iterative way. Training is training is done iteratively. So you would first have a feed-forward pass, as you have seen before when you do a standard neural network. And then there's what's called backpropagation in time. And these are the equations which we're going to derive pretty soon now. So what we are going to need in order to do the backpropagation in time, we will need a derivative of this cost function with respect to this variable c. And now I'm just putting this as a kind of common denominator for all the biases for the different time steps. So we're going to have the gradients of L. We're going to need the gradients of WHH. We're going to need the gradients of WHX. And we're going to need the gradient of WHY of L. So these are quantities which we now need to calculate the derivative of. Now, one of the quantities which can lead to problems, which you will see quickly now, is actually this quantity here. So let me wring that out, because this can lead to what's called exploding gradients, or we can have vanishing gradients. Vanishing. And we're going to see that pretty soon now, why you can run into this type of problems. So this has to do with the way you're actually going to train the network. So let's go quickly back to the Jupyter notebook, because then there are some images which I've taken from the text of Rashka, which hopefully can give a deeper understanding of what is going on. So let's do that, and then we move back to the whiteboard. So let's take a quick look at some of these images, as they hopefully can give a little bit better feeling of the way a typical recurrent neural network is set up. So these images are taken from the text by Rashka. So this is a typical structure of a single layer recurrent neural network. So you would have in every time step here, there's just one single layer with a given number of neurons. But you can have, there is nothing which hinders you in having a so-called multi-layer network. So it means that you can have at every time step, every step X here, you can now have one hidden layer, so you can make this deeper and deeper. And you can see now that these are connected. So we actually connect a previous step with a new step. So that gets information of what happened before, and that shapes the optimization of the next layer. So you're not limited to, let's say, a single layer recurrent neural networks, but you can make them deeper and deeper. So if you look at the layers and the way you actually train and give this information about the sequential aspect, is that each hidden unit receives actually two main inputs, one from the external probe and one from the previous hidden layer. And it's actually this kind of previous hidden layer which can give rise to what normally is called exploding gradients. If we then look at the multi-layer recurrent neural network, this obviously has many more layers in between here, but all these previous time step layers, they conspire to give a final input to the next layer. And you have different ways of sequencing this kind of training which you want to do. So you can have many to one, which is pretty common. So you have a final output, which is that one. So this depends very much on what you're interested in. So the kind of situation which I normally have used is actually the one which I call many-to-many, which you see here. And this is a setup of a typical differential equation solver. So you would have a differential equation solver where you have solutions for a given set of steps here. And then you train a network on that. And you can use this trained network to make a predictions for further time steps. You can also have architectures of many-to-many which look like this. But one of the most common setups is actually this many-to-many, where you have a measurement you're comparing with and some input you have at every time step. And this is something where you could think of this windmill park, where at given time steps, you measure the output from the windmill, the power which is producing, and then you can correlate that with the atmospheric data, the weather data. And then you can keep correcting your windmill park so that it optimizes the output. In that case, you would have the situation which we have here, down in the left corner, many-to-many. That's a typical situation which I've been studying myself. The many-to-one could be that you have many measurements over time, but you have only one observation at the final time. That's another way of thinking of your sequential data. But a pretty common situation is that you have inputs at regular time intervals, like you measuring the pressure of a patient at regular time intervals. So this is a different types of sequencing which you can make. Now, the thing which we're going to look at now is a little bit more in detail, the type of parameters which are getting. And this is essentially what I put on the whiteboard. So we have the parameters here when we open it up. We have this WHH, which feeds in here, as you can see, from one hidden to another hidden. And then you have the connection between the hidden layers and the output. And then you have an input at every step here, which then also gives you a set of weights and biases, as we discussed on the whiteboard. And then this is just a summary of what we put on the whiteboard. And next week, when we're going to build our own code, we are going to look in detail at how we actually set up all the derivatives and do the back propagation in time. So now I'm just setting up the kind of overarching view on it. And then next week, we're going to do the gritty-nitty details. So these are the parameters which we discussed just now on the whiteboard. And we would have the output from this hidden layer, which is then given by an activation function. And then we have this H at a given time. And this is now input into this function here, where the C of Y contains now this output. And then it has a new parameters plus a bias. And this is outputted in here. So we have different bias values, which also become parts of the parameters. And then you have the back propagation through time. So you can think of the recurrent network as a layered feed-forward net with shared weights, and then train the feed-forward net with weight constraints. So you can also think of this training algorithm in a time domain, which is often very easy to do. So the feed-forward pass builds up a stack of the activities of all the units at each time step, and the backward pass that peels activities off the stack to compute the error derivatives at each time step. And after the backward pass, we add together the derivatives at all the different times for each weight functions. And the backward pass is, as before, is actually a linear function in the weights and the biases, which we are training. Now, one thing I wanted to say a little bit towards the end of this lecture is the problem about exploding or vanishing gradients. And the way to see why this is a problem, in particular, if you look at these parameters, which we have here, the WHH. Now, in these images, they have the same labels, but you could think of you training different weights at different time instances. The standard procedure in order to avoid an explosion in memory, which is required, is to train them for just, let's say, the 10 first time steps, and then use the same values throughout the network. That saves memory, and it also saves CPU cycles. Then the idea is that the first steps do a pretty good job in training the network. In general, what you see now is that this, if you think back to a standard feed-forward neural network, which is also very data greedy, this is even more data greedy, and it's even more CPU intensive. So everything here, like it was commented here from you folks, is that every step here, in a way, is like a standard feed-forward neural network. So which are then just connected through these weights and biases. That's the main difference. And clearly, you would now have, if you have 1,000 time steps, you would have 1,000 feed-forward neural networks to train. And that becomes CPU intensive. Next week, we are also going to look at ways to reduce these CPU expenses, which we end up with. But I wanted to just say a little bit about this backward in time here. So we are computing this loss function and or cost function. And in order to do that, we need now to calculate derivatives in order to find the different gradients. So the backpropagation in time for this specific function will, for instance, involve the training of these weights. It will also involve the training of these weights and these weights. But this, if we now use the chain rule, is going to be nothing than us at every time step to calculate the derivative. So this is the gradient at a given time step. So this is part of the optimization. So at every time step or every step, so I'm repeatedly saying time because it's so easy to think of time here. It doesn't need to be time. So it's a sequence of data you have. This could actually, the sequence of data could be you having calculated a function with the equally spaced variables, and then you want to extrapolate to, let's say, infinity. So what you need then is actually to bring back the good old chain rule, which most of you probably saw back in kindergarten. I guess you did that. But this is nothing but the chain rule. And we have to loop over all the times because these W's will also depend on what you have in previous time steps. Because you now have an interdependence between every step here. So if you do that, if you look at this specific function here, and you do the backpropagation in time, you're going to have, when you now look at this quantity, which you see here, this is where the source of problems actually can come. If you look at that one, this is nothing but a multiplication of different time steps. So when you think of the chain rule here, then you need simply to calculate all these different quantities from one given value of k to the final t value here. So that means that you have lots of derivatives which you multiply with each other. This is something you would not have in a standard neural network, because now you're connecting these guys here, these I minus 1 and I, they are at different time steps. And that is what causes a problem with exploding or vanishing gradients. So let's take a look at that, why this is actually a problem, with a simple example. So let's just take this expression. This is the one which causes problems in the training. And let's go back to the whiteboard and look at a simple example, which hopefully can give us a deeper understanding of why this is a problem. So let's look at this exploding gradients and how we can make a simple analysis, exploding or vanishing gradients. Because this can actually ruin the whole training with recurrent neural networks. And you will see a trick which is just called gradient clipping. which means that if the gradient exceeds a certain value, you just put it down to a smaller value, and then you keep iterating. So it's not very advanced, but that's one of the ways by which it is done. So the problem which we have, the problem is mainly with the weights which connect the hidden layers with and the WH and derivatives of the type like this d of h of I with respect to a d of h of k, which is then normally written in terms, because these parameters actually depend on the weights from previous layers up to an n here, the final, over d of h, and then we have the d of h minus 1, I minus 1 here. This is part, which is part, is a part of the evaluation of d of h of I with respect to this parameter hh. So I'm not putting a subscript I on this one just to avoid confusion, because else, so this weights here could be different from layer to layer or from time to time. But I'm not marking that in the equation simply because I already have two subscripts, hh. If I add another subscript or superscript, it's going to look even more messy. But this could also be weights which are shared, or you could have different weights at each time step. But let's just keep it like that. So to see the problem, assume now a simplification. So assume that the weight is the same. So this is what we would call weight sharing. And in order to make things simple, we just call this for W, just to make it the notation a little bit simpler. So what we could say now, and then we leave out the bias to make things simple, leave out bias. So that means that the h of I is actually given by this W times h of I minus 1. So this is the part which links a previous time step with a new time step. And it looks very much like a neural network, right? Because there we had the new layer is given by the previous layer result multiplied with a weight function. Now, if we now look at this, suppose now the weight is the same. So what this means is that I can actually write this h of I as W times W and all the way down to the first value, because the weights are the same. So that means that this could actually be given by W to the power of I multiplied with H0. So keep in mind now, this is not a superscript. This is W I times. Now, the next thing we can do, so this is actually called, if you think of eigenvalue solvers or similar methods, it's called a power method. But suppose now that you can diagonalize this matrix W. So we assume that W is a square matrix. So we assume now that this is something we can diagonalize. W can be diagonalized because we can make a simple analysis here. Diagonalized. So that means that the W can be written out in terms of a magic unitary transformation or orthogonal transformation times a diagonal matrix. So D is diagonal times the transpose. So this is a unitary or orthogonal transformation where we know that this applies, and that's simply equal to the identity matrix. And D is diagonal. So that contains the eigenvalues of W. So this is the eigenvalue matrix. Eigenvalues. And what we say now is that this D has some eigenvalues which go from lambda 0, lambda 1, down to, let's say, a lambda of m. So we assume now that the matrix has dimensionality m plus 1 times m plus 1, okay? So we have such eigenvalues, and then we also assume that, so it means that this W is a matrix, it's a square matrix of dimensionality m plus 1 times m plus 1. Now, what I can do now is to expand in terms of the eigenvectors. So it means that W has an eigenvector set, Wi, which is given by lambda I of Wi here. So if I have that, I can make an expansion of this H0, the beginning. So because I have a linear function, so I can make a superposition and a linear problem. So I have a set of constants, alpha j, which are the overlap coefficients, multiplied with these eigenvectors. So Wj with a subscript is the eigenvector of the matrix W. So this is the eigenvalue problem which you have here. And this forms then an orthogonal basis. And when I have such a basis, I can make a superposition and represent another function in terms of that basis. This is a standard linear superposition principle which you have classically and quantum mechanically. Okay, so if I now apply W on H0 the first time, this is nothing but an alpha j multiplied with W times Wj, and that's become simply j of alpha j of lambda j, the eigenvalue, times Wj. So then I can repeat this many times. So suppose I repeat it t times, then I will have W acting t times on this H0. So that is going to be what I call H of t, the final one. And that will simply now be given by lambda j to the power of t times alpha j of Wj. Now we can assume that the eigenvalues are sorted. So assume now that you have a lambda 0, which is larger than lambda 1, which is larger than lambda 2, and up to lambda m here. That means that in the limit where m goes, or t goes to infinity, so it means that in the limit t becomes large, then this h of t is then going to be equal to approximatively, so it's approaching this value, so it will approach lambda 0 to the power of t times alpha 0 times W0. If this lambda 0 is larger than 1, then the gradients can explode. And we are now soon to the end, can explode. If lambda 0 is smaller than 1, then the gradients can vanish. Because if now you have the same weights and you're repeating this operation till the final layer, then clearly if this t is a large number, then if lambda 0 is larger than 1, then this term can become very large. And if that term is large, there is a risk that when you calculate the derivative, that term can actually explode. On the other hand, if lambda is much, much smaller than 0, after a given time of operations, then this h of t here can actually go to 0. And then when you take the gradient of that quantity can disappear. So this is the problem with the training of the recurrent neural network, either vanishing gradients or exploding gradients. Now, for the problem of exploding gradients, and this is the last thing we're going to say today, there is something which is called gradient clipping. So if you now just define G as a gradient, and this is the last thing today, then we have a recipe which is called gradient clipping. And this gradient clipping is pretty simple to implement if the norm 2 of the gradient is smaller or larger than a given number, where this epsilon is a fixed number by you. So this is just a fixed number. So it becomes a hyperparameter in the setup. Then what you do then is that you let the gradient be scaled down by this epsilon divided by the gradient multiplied with the gradient. And this is one of the recipes which is called gradient clipping, which is commonly used in the training of recurrent neural networks. But you see how you can actually analyze the exploding gradient case if you now think of your weights being the same for all the time steps. So this is a serious problem, and it has often led to actually problems in training of recurrent neural networks. So next week, we are going to discuss different ways of tackling this, but we will also dive into the mathematical details of setting up your own code. But the hope is that you see the basic recipe for setting up a recurrent neural network. And then we are going to look at the details next week. So I want you to have you with me on the more overarching view on the recurrent neural network. I hope that's okay. And then next week, details.